board. Okay, let's see here. Okay, well, at least I kept this note. This morning, I had a nightmare class. I started my Notability, and all of a sudden, all my notes were gone. So that's cool. So I'm just going to kind of wing it today because I don't have anything, and it wasn't letting me download. And then, so I had to do my whole class on the board, which is terrible for me because I got sweaty erasing all the stuff. And then I got in here, and Joya said that her projector hadn't been working, so she also had to use the board. And so it's just a bad day, I think. But it's a good day because the final exam schedule is posted. So that's nice. I mean, it's been posted now for a bit, but our final exam is very late. I know. Boo. How late? It's in the morning, so that's nice. That's all I know, though. December, yep, 18th.
On the actual schedule.
Oh, yeah.
Like 3 different rooms.
They do. Oh, hello. Oops, sorry. I'll talk about the rooms. Let me just mute everyone. Yes, good. And it's from 9 to 12. And it does say C234, C240, and C272. So it's all here. One of those rooms is here. I'm going to try to get us in this room, but it's because there are 2 other sections. I suspect that we are the biggest section, just that popular, you know. And so we're going to take the biggest room, and then the other 2 sections can have their own rooms. But the room, one of these, TBD. And what that means is I have to go and I have to count the seats, which I used to be able to just look up, but then they changed the system after the cyber attack. And now I can't see how many seats are in the room, but I can go in and look and see how many seats. But it's either this one or the one in the corner there. But if you kind of head up here, there'll be signs and stuff, and you know to look for me. So that's helpful, right? And so we'll just be in one of those rooms, and then the other 2 sections can have the other 2 rooms. Okay. So TBD. Once I know which one's the biggest, unless you guys want to be in here, can kind of keep all our stats vibes in one room. I like it that way. So I'm leaning towards our room, but we'll see. We make it work for our tests. What's the difference? All right. So you've got your test back, hopefully. I really dropped the ball on you guys. So I had other tests after you. I haven't posted your grades. I have them. But like I said, it's kind of a sneaky way of making sure that you pick up your test, I guess. Not really my style, but, and I did just forget. And the solutions, I guess. I can't remember if they're up or not. All right. Whew. Anything else that I was going to say? I don't know. How about a little review? Been a while. We started talking about, and it's tough because I usually scroll through my notes to see what we talked about. And now I'll just have to wing it. We talked about the idea behind hypothesis testing. So we introduced hypothesis testing. Which I will, from here on out, abbreviate HT. And even without any sort of formal introduction, we talked about the conditions for hypothesis testing, mostly because they're basically the same as for a confidence interval with a minor change. Okay, and that minor change relies on the hypothesis. And so our hypothesis is going to be whatever we want to either prove or disprove. Now, usually it's what we want to disprove. The hypothesis is what we want to prove or disprove, usually disprove. And we're going to focus for now on the one sample proportion type of question. But then as we have built our skills around the one sample proportion type of question, then we start talking about two sample proportions. How do two sample proportions compare to each other? And then we can go to three or more. And then we can go to, okay, well, what if I have two things in a table, right? And so we're just going to build out. Okay. This doesn't really say disprove, does it? Disprove, there. About the population. Proportion in this case, but in general, parameter. Okay. So we're just talking about one sample proportion. So the hypothesis is going to have two parts. We're going to have a null hypothesis, which is a statement of no change. So the null hypothesis is a statement of no change. That's not very helpful yet, okay? But null means zero, so no change. So the null hypothesis is this original statement. Okay? It's a statement, which I'll underline, which means it's going to take this shape. So it's going to look like this. H subscript 0 denotes the null hypothesis. So null means 0, and so H0 is the null hypothesis. Let's see if I have a different color here. There. So the null hypothesis is a statement, which is why it's really important that you just use a colon and not an equal sign. So many times I see an equal sign here, but that's not true because it's a statement. It's going to be about the parameter, which for now is P, right? Our population proportion. I want to learn about the population proportion. I've taken a sample and I want to compare it to some number. And so here, the equal sign is always in our null hypothesis because it's a statement of no change, right? Or no difference from what we're going to call P naught. Okay. Now P naught, let's see if I can grab I'll use purple. This is called P naught. P naught or P null, but that sounds weird. So I call it P naught, H naught, P naught. So this you can read as H naught. Uh-oh, something got dark on here. And what does that mean? It means we're all good, I guess. I'm on high alert today. Okay. Whew. just need to hang in there for 2 hours. Okay. I'm talking to you guys too, but mostly my iPad. Okay, so H naught, P naught, whatever. H0, P0, doesn't matter. Okay, but I'll call them H naught and P naught. Yeah. Now P naught is whatever proportion, so P0, P naught, is the proportion we want to compare our sample proportion to. We want to compare our sample proportion to. Notice that nowhere in here do we mention the sample. And that's because we know everything that we could possibly want to know about the sample. We can just go and find it, right? And so that was weird of me. I don't know why that caught my eye, but anyways, there. Now it's clear. Just frazzled today. Right? Nowhere in this statement are we hypothesizing about the sample, right? Because we know everything that we could possibly want to know about the sample. You can just go calculate it or look and find it, right? And so what we're hypothesizing about is the full population, right? And so here, this little guy is the population proportion. That's going to change later when we introduce new types of questions, right? But what's nice is my formula sheet has been deleted. That's okay. But on your formula sheet, it's okay. It's okay. Just how can I indicate on your formula sheet? It looks like this. Hypothesis testing for, I guess I can copy it here. It says hypothesis test for P, and it gives you that H naught is P is equal to P naught. How can I make it all? This is on your formula sheet. There. Make it look like I, no, copied and pasted. Okay. So on your formula, on your formula sheet, you have what the default, the skeleton of the null hypothesis is going to look like. Okay. So we did more than that, but I'm not going to call it review anymore. So now let's introduce the alternative hypothesis. Yeah? Because if I have a null hypothesis and I find evidence against that null hypothesis, and we talked about, okay, evidence against the null hypothesis is if I move too far out into the tails, right? And so what we need is, okay, well, what's my backup hypothesis? If this one is not true, right, or if we find evidence against it, then I need an alternative hypothesis. So if we find evidence against H naught, we need an alternative hypothesis. We need an alternative hypothesis. We're going to call it HA. some fields call it H1. You're welcome to call it H1, H0, H1, that's fine. I call it HA. Use a capital A, a lowercase a, it doesn't matter. Okay. But let's see here. Before I do that, let's write out our general H naught, because this is from your formula sheet, right? So then your HA, your alternative hypothesis, has to be about the same thing. It has to be about P and how it compares to P naught. So from there, from your null hypothesis, if you're able to find your null hypothesis, then you have most of your alternative hypothesis as well. Okay? And so here, this has to be about P and P naught. The only change is in the sign, right? And so here, the only change is in the sign. The only change is in the sign. Depending on the question, we have three options for the sign, right? And so the sign can either be not equal to, that's if you want to find, is there a difference? Is there a difference? Is it different from 40%? Is it different from 30%? Right? It could be less than. I'll label it HA signs. Hells Angels. No. So it can be less than, or it can be greater than. This will be from the question. We talked about the p-value, and we're going to talk a lot more about the p-value today. But for now, we're going to have this idea of either a two-sided p-value, where you don't care which direction things went in, right? Versus a one-sided p-value, where you only care about one of the extremes. So this is what we call a two-sided test. And this is what we call a one-sided test. So building your null and alternative hypothesis is going to be what I am going to call just step one, state the hypothesis. Okay, and I'm going to break down hypothesis testing. I use 4 steps. There are others that use 7 steps. They're all the same. It's just how you slice them and dice them. And so you could probably squeeze out 12 steps if you wanted, but I like 4 because it's kind of nice and manageable. And so in a hypothesis test, this will be, and I'm just going to be step 1 in a hypothesis test. I'll outline the steps formally, but for now, that's going to be your first thing. This is where you tell me what you're about to do, okay? And so P naught is also going to be from the question. this has to be a value between 0 and 1 because it's a proportion. A value between 0 and 1, right? It's going to be your hypothesized proportion, right? The proportion we want to compare the sample proportion to. Okay. So all right, depending on the sign of the alternative hypothesis, and because they're so disconnected, because it's going to take us a while until we can find the p-value. We already have the skills to find it, okay? And so I'm going to kind of skip step 2 for now and say, okay, if we talk about our HA signs, let's start with the first one. Whoa, that's nice. I'm going to copy that. I know what you're thinking. That doesn't look that great. Well, it's pretty good for me. But it was too big. Because I need 3 versions. One for each of the signs. So if we have HA is that P is not equal to P naught. Then we're going to have the center, like we saw last day with P naught in the center, our hypothesized proportion in the center. That's going to be the case for all these guys. So I have to assume that my sample proportion came from this distribution until I have proof otherwise. And so that's the general idea of hypothesis testing. And so if we're testing if P is less than P naught, and then if we're testing if P is greater than P naught, what we're going to have is we're going to have some sample proportion. So let's say our sample proportion is somewhere here. In this first scenario. Now, just because our sample proportion happened to be here on the distribution, I would also be concerned if it was at the same distance on the other side, right? And so what happens is I kind of imagine it happening down there as well, equidistant from P naught. Okay. Now, there's an area, there's an area here where my setup is getting glitchy. Okay, it's okay. You're cool. Me. Where we're fine saying, okay, this sample proportion probably came from this distribution. We understand there's a little bit of movement, and so there's this region where we would not reject H naught. We would say, well, it basically is P naught. Okay? And then as we move out further into the tails, we start saying, okay, it could happen, right? Because the tails go to infinity, and so it can happen, right? But the area in the tails gets so small, and the area in the tails is the probability, right? And so if the probability is really small, then that's what makes us say, okay, well, it could come from this distribution centered on P naught, but it's more likely it came from a different distribution that is maybe not centered on P naught, right? So Then from here, we can find the area in both the tails, just because I'm concerned about both directions, right? And so here, the p-value, we need a two-sided p-value if I'm concerned about a difference. We've seen that on our table, right? Where it just took the one-sided p-value and it multiplied it by 2. That's fine, right? So the two-sided p-value is probably the sneakiest, because in the next scenario, if I want to show that p is less than this hypothesized value, well, I better hope that my sample proportion is less than my p naught, right? So then it would end up somewhere down here. Then this area is my one-sided p-value. I can't use 14 to prove that something is less than 3, right? That doesn't work. And so it has to be below p naught. And so that's how you know that, okay, then I need this lower tail area, right? We're always talking about the area in the tail because of the p-value, which I'm holding off on writing out, but I will write out the p-value again, because it's one of those that I want you to potentially memorize until it makes sense. Okay. If I want to show that p is significantly greater than p naught, then I should probably have a sample proportion that's above p naught. So then the p-value is the area in the tail on the other side. Now let's talk about the p-value. Well, I guess this is the one-sided p-value. Okay. The p-value is the probability of seeing something as extreme or more extreme. So the probability is an area under the curve, right? And as extreme or more extreme is what forces you into the tails, right? As what you saw, assuming the null hypothesis is true, so assuming it is centered on p naught, then the p-value is going to be the area in the tail. So it's the probability. And the probability is an area under the curve. The probability of seeing something as extreme or more extreme, which makes it the area in the tail, and what you saw assuming the null hypothesis is true, which is really saying the null hypothesis is that p is equal to p naught. So if p, the population proportion, really is centered on p naught, then that would be the probability. Then we said, okay, by this, then, if the p-value is small, right? And so I'll start a new page here. So if the p-value is small, which I'll kind of what is small? We'll have rules, right? But just as a rule of thumb here, if the p-value is small enough, we have enough evidence to reject H naught in favor of HA. I'll say small enough. Well, small enough is going to be less than some alpha level. So less than the alpha level. This is alpha. It's a little fish. It should be rounder, I guess, like that. Now the default alpha level is 0.05, less than 5%. Okay. But the question, if I don't want you to use 0.05, which is standard across most fields, then I would say use an alpha level of 0.1 or use an alpha level of 0.02 or something weird, right? 0.01. So what does the alpha level look like? If I have P is not equal to P naught, an alpha level of 0.05, because I'm concerned about both the tails, then I would have 0.025 here and 0.025 here. I'd have to split it between the two tails. So what I could do, now we usually don't work this direction, but it might be nice to see it, right? Because what could you do? You could say, okay, well, I can use my table, which I guess I have lost, but now I have found in paper format. This, from the table, is from a Z star of 1.960. And on the other end, negative 1.960. What did I do? I forced the one-sided P to be 0.025, or you can go down to the second line and force your two-sided P to be 0.05, right? And then you can map backwards to find what Z would make that happen. And so really what you could be doing is you could say, fine, any Z that's going to be larger in either direction, right? Kind of tricky with both directions, but any Z larger than 1.96, I am going to reject H naught, right? Because here my Z's are increasing. And as my Z's are increasing, the area in the tail gets smaller and smaller and smaller. And so it would be less than the alpha level. Okay. So what we could do, we could say any P hat more than 1.960 plus minus standard errors from P naught means we reject H naught. Means we can reject H naught. We've moved too far away, and now we have this threshold. But really what we're going to be doing is using the p-values instead. But because we know how Z's work and we're kind of more comfortable with Z's, then I want you to see that you could use those ads as well. And on the test and on the final exam, I don't actually care which method you use. I'm going to use the p-value approach, whereas this approach is called the critical value approach. Doesn't matter. And if you prefer this method, then you can check with me and make sure that you've got it all under control, but the conclusions will be the same. Yeah. It's a little bit easier if you have a one-sided test. So if you have your alternative hypothesis is that P is less than P0, P naught, then all this area would be 0.05. Which means that your Z would need to be less than negative 1.645. And same thing on the upper end for the one-sided. I'll do it the side here. HA if P is greater than P naught, less then 0.05 would be somewhere here. And any Z score greater than 1.645, you would reject H naught. So here, oops, let me use a different color. You're going to reject H naught because you've moved too far out. Reject H naught, and reject H naught. Sometimes called a rejection region. Oops. Okay. Now this concept of kind of moving too far away from my hypothesized center is really difficult. Just in general, the thing about p-values can take some time. It's going to take some practice. And if it doesn't make sense, that's okay. Just stick with it. And eventually it will. Okay. I think we're ready to see the steps of hypothesis testing. I don't really care about the condition, so I'll call it step 0. It's not where any real marks are going to come from. And so you'll just have to kind of know which boxes to check and then we move on. But what are the conditions? Had to be randomly sampled, right? Because we have to assume independence. And we also have that n less than 10% condition. This is the same as for the confidence interval conditions. And if you want, these are called the independence conditions. And then the normality condition. We need n times p naught has to be greater than or equal to 10, which means I need at least 10 expected successes. At least 10 expected successes. And the expected is different from the confidence interval where we just use p hat instead of p naught. But in a hypothesis test, I have this hypothesized distribution that I can use. This requires kind of setting up your null hypothesis before checking your conditions, of course, but that's okay. You're going to have to do it anyways. So n times q naught, which is n times 1 minus p naught, has to be greater than 10, greater than or equal to 10, which means at least 10 expected failures. So the difference here is that you use P naught to Q naught, which is going to be from H naught P is equal to P naught. You kind of have to have your null hypothesis kind of set up in your head at least, which is the next step. So these conditions are always going to check out. It's just we need to know how to check them. Okay. Now, hypothesis testing. 4 steps. Although you'll see why I could make probably 7 steps. Step 1, state the hypotheses. How about this? In dark blue, I'll do kind of extra. And in light blue, I'll do required. Things I need to see for full marks. And then I'll use all the other colors for things around it. Now, you don't have to list the steps. The steps are just kind of to help you. Okay? And so first we're going to state our hypotheses. Now, our hypotheses, from your formula sheet, you know the bare bones structure is going to be P is equal to P naught. But this is going to be some number from the question, just to clarify. Right. Your alternative hypothesis is also a statement, so you want to make sure you have those colons there. Has to be about P and how it compares to P naught, otherwise it wouldn't make sense. And then also from the question, the sign. As a default, we'll use not equal to. Default is not equal to, right? Is there a difference between these two? Let's pause for a minute here. Why would the default be not equal to? If we go back up here, if I have not equal to, then I need to move 1.96 standard errors out before I can reject H naught, right? Whereas for the one-sided, either direction, I only had to move out 1.645 standard errors before I could reject H naught. So it's a little bit easier to reject H naught. Okay? And so to curb that, then you would use a two-sided test if you're not sure. Okay? Even on a test, if you're reading the question and you tell me, hey, I'm not sure, so I'm going to use the default of not equal to, that's fine, right? I'll just take half a mark off because it's something that you should be able to do. But if you follow through with the not equal to, then you're fine, right? So state the hypotheses, right? Grabbing things from the question and setting it up in a formal way. Step 2 is the one that I've been kind of skipping. It's technically calculate the test statistic, but that's hard to say. So I call it do the test. Do the do. Now the test statistic is that Z, right? We want to be able to communicate how far my P hat is from P naught. And so then my Z is P hat minus P naught. This should be hat. There. Divided by the square root of P naught Q naught over N. Which, if we have some hypothesized proportion, then we use it in place of the P hats for our standard error. Okay. So kind of side note here, this is the standard error of P hat in a hypothesis test. This also kind of nudges me in the direction of using P naught to check my conditions. Right? That's more helpful, you know, when we made you memorize all these things. But back in my day, we had to memorize the Z star line and memorize what the areas in the tails were. Not all of them, but 4 of them for sure. 5. Okay, 5. We had to memorize, which is really all you need. So you could do that. You don't have to. I give you tables. Okay. P hat is the sample proportion. How far is it from my hypothesized proportion? Right, taking into account the standard error. Okay. This is also on your formula sheet. I'll do a bigger dot this time. That's what that means. It's on your formula sheet. Which means on your formula sheet, you really have step 1 and step 2 outlined for you. All right. So do the test or calculate the test statistic. I'm saying calculate the test statistic now because later I'll just say do the test, but then I usually get people asking, the question's asking to find the test statistic, and I don't know what that means, but you do. It's just the Z. Okay? So you calculate Z in order to find how far out into the tails you are, right? But like we said, when we use the p-value approach, then we find the area in the tails, right? Pause. Step 3 is going to be find the p-value. Or if you prefer, to find the Z that makes that area in the tail, but I'm just going to stick to this one method for now. Maybe I'll say for the critical value Z star, but not now. Not now. So if you prefer to compare the Z that you calculated to some Z that represents the alpha level, like this, that's totally fine, right? Because the Z that I found is more into the tail than negative 1.645, then I can reject H naught. That's fine. But how we are going to do it is we're going to calculate our Z and compare it to 0.05, right? We can find the area in the tail and we can compare that to 0.05. So find the p-value. This is where I'll frantically go back into my folder and see if it, wow, they're back. Oh, I've never been so happy to see my notes. That is great. Because then I can grab the table. It's almost like it's a fully functioning iPad again. Using the t-table, or you could just call it the table because we just have one table, but it is the t-table because it's the t-distribution. But we're using the z-star line. We find that our z, and I'm going to say z calculated down here, but I'll do it in a different color because it's optional. Green maybe. Z is equal to whatever you calculated from step 2, Z from step 2. So the absolute value of that thing, because we only have positive values, is between some Z star lower and Z star upper. You know how to do that, right? So let's say it's between these two, right? Then the one-sided p-value or the two-sided p-value, I do want you to say which it is, but which it is depends on what? It depends on step 1, your alternative hypothesis, right? Whether you need a one-sided or a two-sided p-value. And so this is from HA, from your alternative hypothesis in step 1. But the area in the tail, you know how to find, is the lower p-value and the upper p-value. I've got an example, so don't worry. There's a lot of ins and outs here. We've done this part before, before though, right? We did it on the test, and we did a lot of practice with finding areas in the tails and using the table to find probabilities. So now, if I know that my p-value is somewhere between two values, right, then I can determine if it's less than 0.05 or not less than 0.05. So step 4 is the conclusion. Now your conclusion always has 3 parts. Always has 3 parts. I smush them into one step, but this is where you could break it up into 3 steps here. The first is the conclusion. Well, first we have to compare our p-value to the alpha level. Okay. And so part one is compare the p-value to the alpha level. The second step, depending on how the p-value compares to the alpha level, right? If the p-value is less than the alpha level, then you have enough evidence to reject H naught, right? And so what we're going to do is we're going to state our conclusion in terms of H naught. And so the conclusion in terms of H naught, there are only two options here. We either have or do not have enough evidence to reject H naught. It's really, really important that you're stating your conclusion in terms of H naught. Why? Because we did all our testing assuming that it was true, right? So then dragging HA into the mix doesn't really make sense. And then the part, because you've done so much work up until this point, this is a long question, right? Typically on a test. And so then the one that people love to forget is the conclusion in terms of the question. What does that mean in terms of the question? And so here, the conclusion in terms of the question. Okay. There are only two options. We only have two options for parts 1 and 2. Here I go again with my distribution. Let's say that we have a p hat down here, and my alternative was that p is less than p naught. Now, if this area is less than, let's make it really obvious, it is just for visualization, less than 0.05, right? Then the p-value, so here alpha is 0.05. So if your p-value is less than the alpha level, then you're past that mark where you're going to start to say, oh, okay, I can probably reject H naught, right? And so here, it's more likely that P came from some distribution that's centered on something less than P naught. Notice that we don't commit to what it might be. We just say, oh, it's probably less than P naught. So then the first option is, and I'll use finally the light blue, since the one-sided p-value, because this is a one-sided test, of course you would write two-sided p-value just to emphasize that you knew to find a two-sided p-value, right? And so here, 1 or 2 So since the one-sided or two-sided p-value of, or I guess we'll have a range, is between P lower and P upper. Right, from step 3, you'll have a range for your p-value. In this case, you'll find that that range is all less than 0.05. And so I'll never make it overlap. And with this table, it can never overlap. And so it'll be on one side or the other. Okay. So since the one-sided p-value is between p lower and p upper, it is less than our assumed alpha level of 0.05. That's the first part, right? Comparing my p-value to my alpha level. Is it less than or is it not less than? And I'm avoiding saying greater than because there's symmetry, okay? And so in this case, it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. If you're rejecting H naught and you're making a formal statement, you should probably say in favor of what, right? In favor of the alternative hypothesis. This is option 1. The other option is, and I'm going to copy this and try to fit it on the next page, I guess. Option. And what I'm going to do is I'm going to mark this up just to highlight the only differences. Option 2. Well, now my p hat is no longer in the rejection region, right? So it's not far out into the tails. And so the change might be something like this. So now I'm not dealing with this, but instead I've got a p hat that's not really that far from my hypothesized proportion. It's still less than it, but it's not significantly less. So then the only change that you're going to say, or a couple of changes, since the one-sided, in this case, p-value is between, it's still going to be between two values, so some p lower and p upper, it is not less than our assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. And if you don't have enough evidence to reject it, you can stop there. So that's why I don't use the term greater than to say it's not less than, because then I can just kind of negate the statements and use the same blurb all over again. Will I have any luck finding, okay, please stay on the line. It'll be worth it, I promise. Well, maybe. Pi day. Maybe here. I promise it's worth it. But Maybe it's not. A. Okay, if this one doesn't have it, I'll give up. It's Snoop. Can I draw it? Probably not. Insert Snoop here. Have to find it. It'll be a surprise. I'll find it later. It's just Snoop, and he says, if the P is low, then the null hypothesis must go. It's not actually what it says. Well, actually, if the P is low, the null hypothesis must go. That's what it says. And it's Snoop Dogg, obviously. Not Snoopy, although kind of funny as well. Anyways, so usually what I find when I'm marking the final exam, especially, it's always written in the margin somewhere on some paper. If the P is low, the null hypothesis must go. All right, so if the P value is low, so if it's less than the alpha level, then you have enough evidence to reject H naught. Yeah? Okay. Hopefully I have better luck finding the example that I was going to do. I do. I think we're finally ready to do an example. Can you believe it? Okay. Just stolen from the textbook. It's believed that nearsightedness affects about 8% of all children. In a random sample of 194 children, 21 are nearsighted. Conduct a hypothesis test for the following questions. Do these data provide evidence that the 8% value is inaccurate? Okay. First things first, let's talk about all the things that we are given. Now, again, what's nice about proportion questions, one sample proportion questions, is we don't need a ton of information, right? In fact, we're given 8% of all children. And that's the value that we want to compare our sample proportion to, right? And so here, we want to compare our sample proportion to 0.08, right? 8%. But we have to do it as a proportion. Which means, therefore, P naught is 0.08. I'll clean this up. This doesn't look like a 0. There. Okay. We're also told that we have a sample size of, my screen just did something, 194. And of those, I have 21 successes. If you wanted to go from that straight to the sample proportion, that's totally fine. But from here, P hat is X over N. So P hat is going to be 21 over 194. And I'm hoping that that's something reasonable. That doesn't really look like it, does it? No, it is not. I'm going to round it to 0.1082. 4 decimal places should be fine. So 4 decimal places. Okay. At first glance, 0.1082 or 10.8% is more than 8%, right? But we want to know, okay, is it far enough away from 8% to be able to say that it's probably the 8% is probably inaccurate, right? It's likely to be something else. And by this, it's likely to be something larger than 0.08. But before we can do that, we have to check the boring conditions. I shouldn't call them that. Step 0 is the conditions. I'm going to be kind of bare bones about it. It says it's a random sample. So I'll put a check mark. Nothing crazy. And less than 10% means, a random sample of 194 children is 194 less than 10% of all children? I think so. So I'm going to do a check mark. I'll explain it. 194 is less than 10% of all children, but you don't have to do that. Then I need to have at least 10 expected successes and at least 10 expected failures. Now that's where the sort of math comes in, n times p naught, which requires us to have an n and have an idea of what my p naught is going to be. So if I have a sample of 194 and the probability of someone being nearsighted in that 194 is 0.08, 194 times 0.08, I would expect 15.52 to be nearsighted. The expectations, you don't do any rounding, you just keep the decimals. So here, which is greater than or equal to 10. Nice. N times Q naught, there's a couple of ways that you could find it, right? If 15.52 are successes out of 194, then what could you do? 194 minus that have to be your failures. 78.48. So here, this is your expected successes and expected failures. Therefore, I'm going to say the conditions for inference are satisfied, which is just an umbrella term. The inference, right, includes confidence intervals and hypothesis testing, but we're going to do a hypothesis test. And so what did we have to do first? I guess I didn't even highlight it. Hypothesis test. And that determined what conditions to check in the second part, I guess. Now we're ready for step 1 of our hypothesis test. I'll put it on the new page. Step 1, state the hypotheses. H naught is that P is equal to P naught. Now I'm going to replace that P naught with the value from the question, right, which we said was 0.08. So I'm going to replace this here with 0.08. I hypothesize that the proportion is 8% or 0.08 until I have proof otherwise. My alternative hypothesis has to be about P and it has to be about 0.08. The only change is it going to be in the sign. Right? And if I paste it in, oh, nice. I'll just grab the question again. Okay. If I want to know if it's inaccurate, right, that means that in my HA, P is not 0.08, it's something else. Inaccurate doesn't tell me is it less than or is it greater than. I don't care. I'm going in both directions. So then here, I have P is not equal to 0.08. I like to make a note up here that this makes it a two-sided test. Okay? Because I later in step 3, so it's going to take a while till we get there, but later in step 3, then I need to figure out, do I need a two-sided or a one-sided p-value? And so here, this is a two-sided test, therefore need a two-sided p-value. And I need the area in both the tails. But again, the stuff they need to write for full marks is in the light blue. I'm sticking to that for this example, at least. Okay. There's a lot of ins and outs with the null and alternative hypotheses, but in terms of the work that you have to show, it's not that crazy. Step 2 is calculate the test statistic or do the test, which is what I'll kind of morph into. From your formula sheet, right, we want to see how far is your p hat from your p naught. And so Z is going to calculate how far is p hat from p naught with a standard error of p naught q naught over n. Oops. That's just math. So let's do it. I'm going to use the rounded value of p hat, which is fine as long as you've kept enough decimal places. P hat 0.1082. Minus p naught, which is 0.08, divided by the square root of 0.08 divided by 1 minus 0.0, or times 1 minus 0.08 divided by 194, I want to say. Yeah. Notice that this is your p naught and your q naught, not your p hats. Okay. 0.1082 minus 0.08, I get 0.0282. And if I do 1 minus 0.08 times 0.08 divided by 194, then square root it, because it's too small, 0.019, 4777168. .0282 divided by that, I get a Z of 1.447808314. Positive, because 10.82 is larger than 8. Makes sense. What's my gut reaction here? I can already tell that I'm not going to reject H naught. Why? Because this is not very far into the tails, right? As a general rule, we have to be at least 2 standard errors out before we can start to assume that we're going to reject things, okay? And so here, my kind of gut reaction is, okay, probably not going to reject H naught, but we'll do the rest of the steps. Okay. So Z, to match the table, we need at least 3 decimal places. And so 1.44, I'll go 8. Unless I find that I'm not, so it's okay. Oh, and I'll do this in need at least 3 decimal places to match the table. Yeah. So that is my test statistic. Now, step, and maybe I'll do it on step 3, find the p-value. It's good to be back. Okay, but it is doing something weird, but that's okay. So here, my Z, 1.448 on the table is somewhere between 1.282 and 1.645. Now, from there, I know, or this is where I need to remember if I have a one-sided or a two-sided hypothesis, right? And so, because that's going to determine if I want the one-sided P or the two-sided P, right? So that's when you scroll back up here. And that's why I like to make a note to myself that this is a two-sided test because I have the not equal to here. And so then I use the two-sided P. So that's all work that you need to do. What do we need to write in step 3? Since, I guess you don't really need the since, but since Z equal to the one that we calculated was 1.448, the absolute value of that thing, I always write the absolute value just because that's safer, is between 1.282 and 1.645. That means the two-sided p-value is going to be between 2 values. Oops, need a different color here. But remember, as your Z moves further out into the tail, the area in the tail gets smaller. So for the p-values, just to avoid thinking about inequalities, I always just use the same inequalities and I always just list them from smallest to largest. So you're going to have to kind of read them backwards. 0.1 is less than 0.2, right? And so we read them this way. But 0.10, 0.20. And you can, of course, use Excel to figure out what the actual p-value is, right? For a Z of 1.448, the area in the upper tail, which means you'd have to do the 1 minus the area to the left, right? But for us, for finding the p-value here, this is what I want to see, which we've already done before, right? In fact, step 2 and step 3, we've already practiced quite a bit, right? Not in this sense, but that's why we had to work on those Z scores and the normal distribution so much. Okay. If it's somewhere between 0.1 and 0.2, how does that relate to 0.05? Notice that the question didn't give us an alpha level, or a significance level is also what it's called. And so step 4 is our conclusion. In this case, it's going to look like this, right? My p-value is not less than the alpha level, okay? And so first I have to compare the p-value to the alpha level. So since the two-sided p-value is between 0.10 and 0.20, somewhere in there, it is not less than the assumed alpha level of 5. So if it's not given, we use 0.05, but just to show off that you know that you're assuming it's 0.05, right? Then you say the assumed alpha level of 0.05. All these things, you're showing off to me all the things that you know to keep track of, right? Is it a one-sided or a two-sided p-value? What is the value, right? It's between 0.1 and 0.2. And then what is the alpha level, right? Just cover all the information that you know. Which means we do not have enough evidence to reject H0. And what does that mean in terms of the question? So then we reword the question as an answer. And sometimes it gets a little clunky. Do these data provide evidence that the 8% value is inaccurate? No, these data do not provide evidence that the 8% value is inaccurate. I'm going to copy this because I can't memorize that on the fly here. Therefore, these data do not provide evidence that the value is inaccurate. All right, just rewording this. And sometimes it sounds weird. That's okay. That's not really the point. It's just you have to restate the question as an answer. Okay. And that's hypothesis testing. You can do that. Let's break up this conclusion into the 3 parts. So the first part, you have to compare the p-value to the alpha level. Compare the p-value to the alpha level. And then, what does that mean in terms of your H naught, your conclusion in terms of H naught? And then, finally, your conclusion in terms of the question. Which is really just reword the question as an answer. And that's the one everyone forgets because you're so tired at that point. Okay. What am I doing? Just enough time to talk about decision errors. So that's a full example. What about decision errors? If I find a small p-value and I reject H naught, there's still that p-value probability that I'm wrong, right? And so there are kind of 2 main errors that can happen. And usually how we copy it from the textbook, sorry, let me just go try to find it because there's a table. I don't want to screw this up. Type 1 and type 2 errors. Here we come, just around the bend. Oh boy. All to steal one little table, this one. Okay. There is some truth out there, right? Some overall population proportion of children who are nearsighted, right? We are saying it's basically 8%, but maybe it's actually 8.13 or something like that, right? We don't know because we don't collect the entire population. But there is some truth here if we were to collect the entire population. And so here, if we collected the entire population, we don't need to do that. But if we were to do that, then there is some truth out there. The problem is that, okay, our test conclusion, if I do not reject H naught, there's a chance that HA is true, right? There's a chance, and we call that a type 2 error. Type 2 errors are not terrible, but if you reject H naught in favor of HA when you shouldn't have, that's what we call a type 1 error. And all the textbooks, although I will admit they never really made sense to me, like in a jury trial, right? You have to assume that someone is innocent, which is H naught, right? Assume they're innocent until they're proven guilty, right? HA. But if H naught is true, and here I am using it anyways, I guess. If H naught is true, so if they're innocent, then if you say then they're innocent, that's okay. It's not great, but it's okay, right? It's better than the alternative where you say, hey, they're guilty when they're actually not, right? That's bad. Both of those are bad, but it's kind of a bigger bad. Right? And so same thing for hypothesis testing. If you reject H naught when you shouldn't have, that's bad, because often rejecting H naught means that you're saying, okay, my I don't know, my sales are significantly higher than my peers' sales or something like that, right? When maybe that's not true, right? And so usually what we try to do is we control the type 1 error rate which is the alpha level, which is also called for the significance level. Right? Because the alpha level set that threshold of, okay, how far out do you have to be in order to reject H naught, right? There's still some probability that you're wrong. And when we set the type 1 error rate or the alpha level, really what we're saying is, I'm okay with making a type 1 error 5% of the time. Yeah? And so the default alpha level of 0.05 really says I am okay making a type 1 error 5% of the time. We only do it once, so it doesn't really make sense, but kind of the gist of it. Okay. Now, a type 1 error, right, is when you reject H naught when you shouldn't have, which means that the only time that you can make a type 1 error is if you reject H naught, right? If you reject H naught and HA is true, then that's fine. That's okay. That's not an error, right? And if you do not reject H naught when H naught is true, then that's also not an error, right? And so the only error is if HA is true. Only 4 possibilities. Yeah. But we try to control the type 1 error. Yeah. And so let's see here. There was something else I wanted to say. Type 1 errors. That's what I wanted to say. This is why we never accept a hypothesis. If I see the word accept, I get mad. I don't want to see it. Now it's kind of like I've incepted it. That's why we never say we accept a hypothesis. There is always a probability that we're wrong. Okay? I never ever want to see the word accept. Makes me think. So I love steep tea at Tim Hortons, and I always just get 2 cream. And so when my husband and I first started dating, he would say 2 cream, no sugar when he would order for me, because he wasn't used to. Anyways, and so, but then I would freak out and I would say, no, you said sugar. And then all they would hear is sugar, and they would put sugar in my tea. And it just ruins it. And so then we always joke now that sugar today, I'll have none, but they just enter sugar. So now I'm worried that I've done the same thing with accepting a hypothesis, but we never, if I see the word accept, no. I know, harsh. You either have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. Sugar, today, I'll have none. We either have enough evidence to reject H naught, or we do not have enough evidence to reject H naught. Those are your only 2 options. Okay. Notice the difference, right? Have enough evidence to reject H naught is also acknowledging that, okay, I could be wrong, right? Or I do not have enough evidence to reject H naught, which kind of ends the story. Which is also where I'll end the story of hypothesis testing. And we'll start chapter 6, so 6.1 on Thursday, which is just more one sample proportions. I'm going to show you how to calculate a sample size, and then we'll keep moving. If you have any questions, let me know. Otherwise, I'll see you on Thursday.
I do have a question for you.